Welcome to Selection with Sathi. Today we will master AVL trees and rotations with code on screen. A regular BST can become skewed and degrade to OFN operations. AVL trees solve this by automatically rebalancing after every insert and delete. We will cover the balance factor, all 4 rotation types, and work through detailed dry runs. This is one of the most frequently tested topics in GATE CSE. Let us begin. Let us start with the AVL property. An AVL tree is a binary search tree where every node maintains a balance factor. Look at line 11. The balance factor is height of left subtree minus height of right subtree. This value must be -1, 0, or +1 for every single node. If any node has a balance factor of +2 or -2, the tree is unbalanced. We fix it using rotations. Look at line 6. Each node stores its height, which we update after every operation. The function getHeight on line 8 returns -1 for a null node. This guarantee of balance ensures the height stays O of log n. The LL rotation, also called right rotation, handles the left-heavy case. When a node Z has balance factor +2 and its left child has balance factor +1 or 0, we perform a single right rotation. Look at line 2, Y is Z's left child. Line 5, Y's right subtree T3 becomes Z's left subtree. Line 4 is not shown but implied. Y becomes the new root with Z as its right child. Actually look at line 5, Y dot right equals Z, line 6, Z dot left equals T3. Lines 8 through 11, we update heights bottom up, Z first then Y, line 12, return Y as the new root of this subtree. This is a single rotation, just O of 1 pointer changes. The RR rotation, also called left rotation, is the mirror of LL. When node Z has balance factor -2 and its right child has balance factor -1 or 0, we perform a single left rotation. Look at line 2, Y is Z's right child. Line 3, T2 is Y's left subtree. Line 5, Y becomes the new root, Z goes to the left. Line 6, Z's right pointer takes T to the subtree between Z and Y. Heights are updated in lines 8 through 11, bottom up. The structure is identical to LL rotation but mirrored. Once you understand one, the other follows naturally. The LR rotation handles a tricky case. Node Z is left-heavy with balance factor +2. But its left child is right-heavy with balance factor -1. A single right rotation will not fix this. We need a double rotation. Look at line 3. First, left rotate Z's left child. This converts the problem into a standard LL case. Line 5, now right rotate Z, just like a normal LL rotation. The two steps together fix the imbalance. Lines 8 and 9 in the comments explain. Z has BF +2, Z dot left has BF -1. Whenever you see this combination, apply LR rotation. The RL rotation is the mirror of LR. Node Z has balance factor -2, and its right child has balance factor +1. Look at line 3. First, right rotate Z's right child. This converts the problem into a standard RR case. Line 5, then left rotate Z 2 rotations, and the tree is balanced again. An important fact, after an insert. At most one rotation fixes the entire tree. But after a delete, you may need rotations at multiple ancestors, up to O of log n. This is a subtle difference that Govt sometimes tests.
Let us trace insertions into an empty AVL tree. Insert 30, it becomes the root. Balance factor is 0. Insert 20, goes left of 30. BF of 30 is plus 1. Still balanced. Insert 10, goes left of 20. Now BF of 30 is plus 2. Violation. Check the left child 20, its BF is plus 1. BF plus 2 at Z and plus 1 at Z dot left, this is the LL case. Right rotate 30, note 20 becomes root, 10 is left, 30 is right. Now insert 25, goes right of 20, then left of 30. BF of 30 is plus 1. Fine. Insert 28, goes right of 25. Now BF of 30 is plus 2. Check left child 25, BF is minus 1. That is LR case. Left rotate 25, then right rotate 30. Final tree, 20 with children 10 and 28 has children 25 and 30. Now let us delete a node and rebalance. Starting tree, 20 with left child 10 and right child 28, where 28 has children 25 and 30. Delete node 10. It is a leaf, so simply remove it. Now node 20 has no left child and right child 28 with height 1. BF of 20 is minus 2. Right heavy violation. Check right child 28, BF is 0. BF minus 2 at Z and 0 at Z dot right, this is the RR case. Left rotate 20, node 28 becomes root, 20 goes left of 28, 25 goes right of 20. Final tree, 28 with children 20 and 30, where 20 has right child 25. All balance factors are now valid. Why is AVL tree height guaranteed O of log n? Let us look at the minimum number of nodes n of h for a given height h. N of 0 is 1, just the root. N of 1 is 2, root plus 1 child. For height h, the formula is n of h equals 1 plus n of h minus 1 plus n of h minus 2. This is because one subtree has height h minus 1 and the other has height h minus 2. This recurrence is very similar to Fibonacci numbers. So n of h grows exponentially, approximately as phi to the power h, where phi is the golden ratio 1.618. Inverting this, h is at most 1.44 times log base 2 of n. That proves AVL height is always O of log n. How does AVL compare with red-black trees? AVL trees are more strictly balanced. Height is at most 1.44 log n. Red-black trees allow up to 2 log of n plus 1 height. So AVL trees give faster searches because of shorter height. But AVL trees require more rotations during insert and delete. Red-black trees need fewer rotations, making them faster for frequent modifications. In practice, AVL is used in databases where lookups dominate. Red-black trees are used in language standard libraries like C++, stdmap, and Java tree map where inserts and deletes are frequent. Gate questions may ask you to compare the two.
Quick exam tips. First, balance factor must be -1, 0, or +1 at every node. Any violation means a rotation is needed. Second, after an insert, at most one rotation, single or double, fixes the tree. After a delete, you may need rotations at multiple ancestor nodes. Third, AVL height is at most 1.44 times log 2 of n. All operations stay O of log n. Fourth, for gate rotation questions, first find the node with BF plus 2 or minus 2, then check its child's BF to determine LL, RR, LR, or RL. For more DSA concept videos with code on screen, download the Selection with Sathi app. Like and subscribe. Thank you.